We introduced new projection mapping techniques under environmental lighting by replacing room lights with heterogeneous projectors. Projection mapping is a technology that allows computer-generated images to be superimposed on a target object in physical space using projectors. Previous studies have investigated the utility of projection mapping in a range of fields, such as product design. However, there is a strong and crucial constraint in projection mapping: images need to be projected in dark environments. Typical environment lighting globally elevates the scene brightness. Therefore, if projection mapping is performed under it, the dark areas of a projected result inevitably get brighter, which causes significant contrast degradation in the projected result. We overcome this limitation by replacing conventional room lighting with heterogeneous projectors. These projectors replicate environmental lighting by selectively illuminating the scene, excluding the projection target. Typical environment lighting globally elevates the scene brightness. Therefore, if projection mapping is performed under it, the dark areas of a projected result inevitably get brighter. We propose substituting multiple projectors for typical room lights to selectively illuminate the scene, while excluding the projection target, as a means of overcoming the dark environment constraint of projection mapping. Projector-based environmental lighting enables us to avoid undesirable increases in global illuminance on the target surface. Consequently, we can mitigate the contrast reduction caused by typical environment lighting. Surrounding of the projection target, we propose the use of a custom projector with a much larger aperture than existing off-the-shelf projectors to illuminate the environmental surfaces surrounding the projection target. Aperture size of a projector affects the emitted ray intensity and the appearance of a shadow. As shown in the left, a standard projector is a point light source producing a high luminance ray and a hard shadow. As shown in the right, the proposed large aperture projector is an area light source creating a low luminance ray and a soft shadow. This shows the difference in shadows created by a standard projector and our large aperture projector. The illumination produced by the standard projector appears to result from directional light, which is inconsistent with common diffuse environmental lighting. In contrast, the illumination produced by the proposed large aperture projector seems to reduce the perception of directional light. The experimental system includes a sofa, desk, and other furniture to recreate a typical living room. Additionally, we place small objects on the desk and bookshelf, including a white bust statue on the desk to serve a projection target. For capturing the scene, we used a camera positioned at the edge of the room. We employed 6 projectors as luminaire projectors, comprising 5 standard projectors and 1 custom-made large aperture projector. The large aperture projector, comprising an LCD display and a large Fresnel lens, provided illumination for the desk. All of these projectors and LED lights were mounted on the ceiling. We introduce a novel distributed optimization method for multiple projectors that determines the projector pixel values to accurately reproduce the illuminance and chromaticity incident on surfaces under typical luminaires. Leveraging the spatially low-frequency nature of environmental lighting, this technique computes pixel values more efficiently than a conventional pixel-wise radiometric optimization framework. Furthermore, this method takes into account the interreflection of projected light between adjacent surfaces. This is the demonstration of our system, the white bust statue positioned on the desk before and during projection mapping of a crack pattern under typical room lighting with LED lights, and then under dark room, and under the proposed environmental lighting using projectors. We substitute multiple projectors for typical room lights to selectively illuminate the scene, while excluding the projection target, as a means of mitigating the reduction in contrast under environmental lighting. Before texture projection, we demonstrate that our method can selectively remove environmental light from the target object, while typical lighting significantly increases the brightness of the target. The projection mapping results demonstrate that our method can manipulate the target's appearance under environmental lighting, while minimizing the intensity elevation in dark areas of the projected texture compared to the typical lighting. We altered the surface material of the target object to a mirror-like glossy material using projection mapping under the same 3 lighting conditions. The projection mapping result in the proposed method exhibits higher contrast than the typical lighting condition, and the surrounding environment remains visible. As a result, the projected bust statue can be perceived as having a glossy material to the greatest extent under the proposed condition. We conducted user studies to investigate how much the proposed method affects the observer's perception in the visual system. In User Study 1, we investigated how much the proposed method affects the observer's perceived color mode. We used the bust statue as the projection target and presented the projection mapping results of 4 projection images, as shown in the slide. In the figure, surface color mode means the projected object is perceived as illuminated, while aperture color mode means the projected object is perceived as self-luminous. A Wilcoxon-signed rank test showed that there was a significant difference between scores given for the proposed replicated environmental lighting compared to the dark room condition when the crack pattern was projected. The first user study confirmed a tendency for observers to perceive the projection mapping results as illuminated when using the proposed environmental lighting. In our second user study, we evaluated our large aperture projector as a luminaire for illuminating the surrounding environmental surfaces of the projection target, comparing it to a standard off-the-shelf projector. The participant was asked 2 questions and answered on a 5-point scale questionnaire. A Wilcoxon-signed rank test showed significant differences between the scores given for the proposed projector condition compared to the standard projector condition in both questions. Specifically, the environmental lighting provided by the standard projector was perceived as significantly more directional than that provided by the proposed large aperture projector. Additionally, the participants judged that the illumination by the standard projector disturbed the communication significantly more than that by the proposed projector. Through the second user study, we confirmed that selecting a large aperture projector as the luminaire for illuminating the surrounding environmental surfaces of the projection target is crucial to creating a lighting environment familiar to users and minimizing disruptions during their tasks. This is the summary of our study. We introduce a novel environmental lighting framework that replaces typical room lights with a combination of heterogeneous projectors to address the dark environment constrained in projection mapping. We developed a distributed optimization method for the projectors to accurately replicate the environmental lighting of typical luminaires. We employed a large aperture projector as an area light source to illuminate the surrounding environmental surfaces of the projection target. We confirmed, through user studies, that observers perceive that the projection mapping in our system alters the reflectance properties of the target surface as if under typical luminaires. As part of our future work, we have 2 technical limitations. When the user approaches the projection mapping target, hard shadows are cast over it, and, for distributed projector optimization, a stably fixed camera is needed.